NMR Spectroscopy. This is chapter 13, and this is your brain. In the evening, we're all tired. All right, NMR, nuclear magnetic resonance. Nuclear magnetic resonance is a form of spectroscopy that measures the property of certain nuclei. Now, when you look at the quantum description of a nucleus, one of the properties it can have is something called spin. Now, that doesn't really mean that it is figurative, literally spinning, but you can imagine that it is. NMR exists because the quantum property of spin, and we'll see how that works in just a minute. The image that we saw initially was a medical MRI. Now, you've probably all heard of that. MRI is nothing but an NMR, actually, except when it was being developed, they decided that the public did not like the word nuclear in the name. Therefore, they dropped it and called it magnetic resonance imaging. Same thing, though. All right. An element will be NMR-active. That means it will be sensitive to an NMR spectrum if it has an odd number of protons, odd number of neutrons, or both. These nuclei will exhibit an angular momentum characterized by a spin quantum number, abbreviated I. If I equals 1/2, the nucleus itself will be sensitive and can be studied by the NMR. If the nucleus, if the spin number is 0, it's NMR silent. Now, spin of 1/2, that includes the hydrogen, carbon-13, fluorine-19, P31. Those are all very useful things. A spin of 0, carbon-12, oxygen-16, etc. So common carbon and common oxygen really aren't going to show up in the NMR, but proton and carbon-13, those are the ones we're going to deal with, will. If you imagine that the nucleus really is a charged body and it is spinning, you can easily imagine that it will generate a small electric and magnetic field. In NMR, we're going to take these nuclei that are supposedly spinning, and we're going to align them in a magnetic field. Now, originally, all of these are random. This is supposed to represent where the fields are pointed, and they're all random. We're going to take this group of nuclei and put them in a very powerful magnetic field. When we do, we apply a field this way. These nuclei will either line up with the field or against it. Now, with the field is a lower energy state. Against it is slightly higher energy. So we turn on our magnetic field, and these guys reorient. So here we have what we'll call +1/2 and -1/2. Because the orientation with the field is slightly lower energy, you will have a tiny excess population in the +1/2 orientation. All right, so what we've done so far is just take a bunch of nuclei, stick them in a magnetic field, and the spins align either with or against the field. Now we're going to take and apply an RF signal. RF radiation, if it's just the right frequency, will interact with this nucleus and induce what's called a spin flip. That is, things that are oriented up will absorb energy and they'll flip, so they're oriented down. Same thing with these guys, they'll flip so they're up. So here comes our RF, and everything undergoes a spin flip. Now, because there's slightly more nuclei in the lower energy orientation, that means that this is going to be show up as a net absorbance of this RF energy. So we know how much energy we're putting in. We get the spin flip. Some of it has been absorbed, and we can measure that. That is what we measure in the NMR. Now, let's see. Okay, this is what I said. Lower energy alignment, some RF is absorbed, and that can be measured. Now, if all of the nuclei in a compound underwent spin flip at the same energy, NMR would be useless. However, compounds have electrons. Electrons, depending upon how many electrons you have around the nucleus, close to the nucleus, whatever, shield it somewhat from the magnetic field. The frequency at which resonance occurs depends upon the electronic environment surrounding the nucleus. Valence electrons tend to shield the nucleus from the RF field. The extent of the shielding is described as the chemical shift of a given nucleus. We represent it by the Greek symbol delta, lowercase, and we describe it in terms of parts per million, ppm. ppm actually has to do with a measure of the frequency that's being shown on the particular nuclei. This is what a very simple, stupid NMR would look like. In the old days, anyway. This is a continuous wave, it's called. We have a nice big honking magnet. Your sample goes in this little tiny tube. It's about 1/8 of an inch across. When you put it in, you spin the sample very, very fast, and that guarantees homogeneity throughout the field. This represents the RF oscillator that we're going to put the energy into it. And we wrap it with a detector coil so that we can figure out exactly what frequency is being absorbed. Let's talk about C13 NMR first. C13 has a spin of -1/2. The problem with C13 is, however, that it only represents 1% of the carbon that we have typically in our compounds. So it's a very low isotopic abundance, only about 1%. This is what a nice big modern NMR spectrometer would look like. This is the magnet. It's actually supercooled with liquid nitrogen. Got a big honking magnet in there, computer, etc. It's, lots and lots of work. Very fancy machines, very expensive. In C13 NMR, we're going to be looking at the carbons in carbon compounds. The chemical shift down here, delta, is going to vary depending upon the electronic environment of the particular carbon. We're going to look at the absorbances as we go from, say, 0 to 200 parts per million, and we're going to try to correlate those with structural features. So let's start up here at the very top. We're up right around 200 or so. The carbons that absorb at the highest chemical shift, that is, are the most deshielded, are going to be the carbonyls. Among the carbonyls, ketones and aldehydes are the most highly shifted. Ketones are typically 210-ish. Aldehydes slightly less, right around 200. The rest of the carbonyl groups, the acyl groups, carboxylic acid, ester, amide, acyl halide, and anhydride, these guys all come, typically around 170 something. So it's very easy if you have a carbonyl in your compound, you can classify it as ketone aldehyde or acyl very quickly, just by its chemical shift. Going down, the next thing we hit are going to be carbon-carbon multiple bonds. Now, in the region of carbon-carbon multiple bonds, the highest in terms of parts per million are going to be your benzene carbons. We'll see that there are particular patterns of these depending upon substitution, but they tend to be here between 150, maybe 130, somewhere in there. Again, depending on what's attached to them. The carbon of a nitrile is fairly highly shifted. It'll be down here in the 130s or so. Simple double bonds, depending on what's attached to the double bond, anywhere from 100 up to 140. Triple bond of an alkane isn't shifted very much. It's around 80, 70 to 80, something in there. The next group we hit are carbons that are adjacent to electronegative things. That's going to be this little group right here. I've shown a CH2 with a chlorine, a bromine, and an oxygen. Of these, the oxygen is the most electronegative, and it shifts the highest, so it'll be closer to 70-ish, if you will. Chlorine is more electronegative than bromine, so it's typically a little higher than the alkyl bromide would be. C13 is also sensitive to crowding. It's a steric effect. Down here in this region where we have simple CHs, you'll note that simples are down here around 20, like a methyl group. A secondary carbon will be higher, between 30 and 40. And between 40 and 50, typically we will get tertiary. The more stuff you put around the carbon or close to the carbon, the higher the shift tends to be. So this is our basic range. We're going to look at these guys. Again, carbonyls down here, double bonds more or less in the middle. These are next to electronegative groups, and simple carbons down here at the bottom. Any questions? Well, this is always easiest if you just do it. So let's look at a compound. This is 3-methyl-2-butanol. If we look at this, the first thing we should say is, this is a simple ketone, isn't it? Because it's a ketone, we would expect that carbon to be very highly shifted, maybe up around 210-ish or so. This is a very simple methyl group. It is, however, attached to a carbonyl carbon. Because it's attached to the carbonyl carbon, which is somewhat electron withdrawing, it'll be shifted down a bit. Probably, around 30 parts per million. That's 30 delta. One thing that you need to be very aware of in C13 is symmetry. We have an isopropyl group here. Now these two methyl groups are identical, aren't they? They're identical. They're both attached to the same carbon. Little plane of symmetry here separating the two. That means they're going to show up as a single absorbance. We also have a secondary carbon here in the middle, so these are going to be simple, and the secondary is going to be crowded out a bit. So with a secondary, we might expect to be at 35 to 40. And the simple primaries here, oh, probably less, maybe down around 20-ish. So that's our prediction. Any questions on how we did that? Just ballparking all these things as we go. So let's look at it. This is the C13 spectrum. Now actually this is what's called a proton decoupled spectrum. But we'll talk about what that means in just a few minutes. Right now let's just look at the chemical shifts and see what we really have. For our carbonyl, we said around 210. It's actually around 212. Here's our secondary carbon. It's about 41, 42. We have our simple methyl here next to the carbonyl. So it's scooted down a bit here to about 27. And finally, our simpler methyl groups here on the end show up at about 17. If we did this backwards, we would, not knowing what this is, we would look at this spectrum and say, okay, clearly we have a ketone carbonyl. We have 3 other types of carbons. This is either crowded or it's next to there, and this is a simple. So that's the kind of information we get just directly by looking at it. Let's go ahead and look at some compounds and try to predict more or less what we might expect in the spectrum. Now, like I said, the first thing that you always want to do when you look at a compound for NMR is to think about symmetry. The game that we tend to play is called, how many peaks would you expect in the proton decoupled NMR for a given compound? How many unique carbons are there? So let's look at our first one here. Is there a plane of symmetry here? Well, absolutely. We can split this guy right down the middle this way. We have 3 carbons on both sides, and they're identical. So how many peaks do we get in the C13 NMR? We would get 1, 2, 3. That's step 1. Now let's look at each of our carbons and just try to guess more or less what the shifts might be. The terminal methyl, that's going to be pretty simple, isn't it? That's going to be 20, maybe a touch less. We go in here to our secondary. That's going to move up a bit, maybe 30-ish or so. This is also a secondary, but it's getting in here in the middle of the molecule. It's a little crowded. So that's going to be moved up a little bit more. So that's our anticipation. Our simple primary here, 10 to 25. Our secondary, 20 to 40. And this guy that's crowded, well, probably 30-ish. Just as a ballpark. This is what it actually is. Down here, our terminal carbons are about 14. We go up to 22 and up to 31 for our interior secondary. 3 peaks, all in the simple range, moving from simple methyl up to hindered interior or methylene. Any questions? Look at this guy. Do we have any sort of symmetry here? Well, there's no real molecular symmetry per se, but we have an isopropyl group, so these 2 methyls are the same, aren't they? If we look at groups here, that's going to be a simple methyl. These are going to be simple methyls as well. We expect 5 peaks. 1, 2, 3, 4, 5. Our simple primary down here, between 10 and 25. Same thing over here. Remember, these two are the same. We have a secondary, another secondary, and we have a tertiary. Our first secondary, probably 20 to 40. Our next one, crowded up a bit, so it's going to be a bit higher. And our tertiary should be a little bit higher than that. So that's what we expect. Any questions? Well, let's see. We have a nice simple here at 14. These guys actually show up a bit higher because this whole end of the molecule is pretty crowded, and that shifts them up a little bit. Here's our simple secondary. This is a nicely crowded secondary. It's even more than our tertiary. So lots of crowding issues in C13. How many peaks? Is there a plane of symmetry? Of course there is. Split this guy right down the middle. So how many unique carbons on each side? You want to say 3, but you're wrong, because these two methyls are going to be the same, aren't they? So that's 2. All right. These methyl groups on the end are going to be simple. Going to be a real crowded molecule, so it's going to be a little higher than the simple methyl group. And we have these guys, which are tertiary. Our simple, we expect it down at the bottom. Our tertiary is going to be higher. In fact, we have 20s and 34 for our tertiary carbon. Look at the next one and tell me how many peaks. Well, these 3 methyl groups are all going to be the same, aren't they? So that's 1. Have a quaternary carbon here, that's 2. Secondary is 3, primary is 4. We're looking at 4 peaks in the spectrum. Again, we have a simple methyl on the end here. We have 3 more or less simple methyls down here. They're going to be moved up due to crowding. We have a secondary sitting here. And our quaternary is going to be moved up quite a bit, probably due to lots of crowding. That's what we think. In fact, this is what it looks like. Methyl groups and the quaternary are just about the same because this is just one big honking ball. If you think about what a trimethyl substituted carbon looks like, great big ball, butyl thing. Here's our secondary, and way down here we have a 7 for our simple primary. Any questions? Well, let's just look at some electronegative groups and see what the effects of those are. These are basically all ethyls, except this guy, of course. We have bromine. We're going to look at this carbon here. Because it's adjacent to a bromine, it's going to be shifted down. Probably not as much as this guy is adjacent to the chlorine. For the first one here, our bromine shifts the secondary down to about 34 or so. The chlorine shifts it even more because it's more electronegative, down to about 45 or so. A nitrile group is fairly electronegative by itself. This carbon here, remember, is going to show up down in the triple bond region. And because it's a nitrile, it's going to be very polar. So this carbon is going to be shifted way down, probably in the hundreds or so. It's actually 117. And the CH2 next to it is shifted up from, where it should be, just up a little bit to about 23, 24. Oxygen is more electronegative than chlorine. And the effect of oxygen is to shift things even more. So we expect this to be shifted more than our 45-ish. And in fact, it's moved all the way up to 88. Simples on the end, and these are secondaries. Again, the oxygen in the middle, going to shift these guys. These are up to about 66 or so. Finally, for our tetrahydropyran ring, these carbons here are going to be shifted just about like these guys were, and the rest are simple secondaries. Any questions? Take-home lesson, electronegative groups, move it downfield, typically in the 40 to 60 range. Carbonyls. We talked about carbonyls. Remember, in carbonyls, we're going to have two classes, ketones and aldehydes, and acyl. So this is a ketone. We would expect that to be 210-ish. 207, that's close enough. Simple aldehyde of acetaldehyde. This is going to be right about 200. So ketones are shifted the most, aldehyde just slightly less. This is an ester. Now the ester is an acyl derivative. These are going to cluster very nicely in the mid-170s. So it's really easy to tell the difference between an acyl carbonyl, 171, and a ketone or aldehyde above 200. Carboxylic acid, the same thing. And an amide, just about the same thing. If we take, this is a ketone carbonyl, but we've put a double bond here, so it's conjugated with it. If you have a conjugated system, it will tend to move the chemical shift down. So instead of being around 210, this is going to drop down, maybe close to 100 or 200, something like that. It's still up above the acyls, but it can drop down. Any questions? Let's look at one final group, and this is our multiple bond group. Remember, these come down below the benzene ring. Benzene rings are the highest in this group. And these will be in the mid-100s, 125 for a simple alkene like this. There's a diene. Interior slightly higher due to steric, 116 on the ends. Triple bond. Triple bond carbons are shifted the least of our double and triple bond group. One exception, of course, was the nitrile. Remember, that was around 100 or so. That shifted a lot. Here's a simple triple bond, and I particularly want to show you this effect. The carbons, again, in the 70 to 80 region, like you might expect. But look at this thing on the end. The pi cloud of an alkyne shields an adjacent carbon very, very strongly. Shields it, all the electrons shield it from the magnetic field. This winds up literally at about 1.5. This one, about 10. It's an interior, so it shifted up from that, but it's still really down there. Triple bonds are really good at doing that. All right, let's look at benzene. One of the neat things that we can get from C13 is we'll be able to look at the C13 spectrum and tell what things are attached to a benzene ring, at least their relative orientation. So here we have a monosubstituted benzene. Overall, they're going to be in the region of 120 to 160. And they're kind of separated from the alkenes, they're separated from the carbonyls, so they're usually easy to pick out. Step one, how many peaks do we expect in the NMR here? How many unique carbons do we have? Well, we can split this thing right across the middle, can't we? That means that these two carbons and these two carbons are the same. So we're going to have our methyl group, going to have this guy, which is attached to the methyl group, this guy that isn't, and then two more. This is what our distribution looks like. 4 peaks in the aromatic region and the methyl group. Here's our first carbon, 137. This carbon, 125. These two are 128, and these two are 129. Total of 5 peaks, 4 in the benzene or arene region. So let's play the game again. How many carbons, how many unique peaks will we get in the arene region for this guy? Look for symmetry. Because we have methyl groups on each end, this is a symmetrical 1,4 disubstituted benzene, isn't it? That means we have a plane of symmetry this way. This half is the same as that half. And we also have a plane of symmetry this way. Top is the same as the bottom. So, how many unique carbons do we have in the benzene region? Well, we're going to have one that's attached to the methyl group, same as this one, and we'll have one up here. We will have 3 peaks in the overall NMR, our methyl group, the carbon attached to the methyl, and then the ring carbon. All the ring carbons here are 129, 134, and our methyl group is about 22. How about this one? How many peaks in the NMR? Come on, you guys survived chapter 5, which is stereochemistry. You can do this, right? It's just simple symmetry. We can take and split this guy right in half this way. These two and these two are the same. We have a carbon attached to the methoxy group, one that isn't, and 2 ring carbons. We expect a total of 5 peaks. Methyl group up here is shifted because of the oxygen. We have a 162, a 120, 129, and 114. Finally, let's do one more. How many unique ring carbons will we see here? Well, because we have a methyl and a methoxy, this carbon and this carbon are different, aren't they? Likewise, this one is sitting in between these two, so it's unique. This is closest to the methyl, this is closest to the methoxy, and this guy's just kind of dangling out here by itself. There are 8 peaks in this total spectrum, 2 for the substituents, and we can see each of the ring carbons separately. One more. Now, both of these are methyl groups. That makes it easy. Go ahead and draw your plane of symmetry, because there is one, and just simply count your carbons. There's our plane of symmetry. This is going to be 1 unique carbon. That's 2. That's 3. Our methyl groups are identical, so a total of 4 peaks in the NMR. Our methyls at about 20, 138, 129, and 125. So when you look at a compound and you're trying to figure out its carbon-13 NMR, again, the first thing you want to do is look for symmetry. Try to figure out how many peaks you expect. Then you go and you look at the environment, you look at the functional groups, and kind of spread them out over the part per million scale. Really not too difficult. All right, let's look at our first complication here. These carbons are attached to hydrogens, aren't they? Now, we said that very early on, anything with a spin of 1/2 was going to be NMR active, wasn't it? Carbon-13, which is what we're looking at here, is indeed spin of 1/2 NMR active, but so is the hydrogen. So when we take a compound and we stick it in the magnetic field, not only the carbon nuclei are going to be oriented, but the hydrogens are too. This leads to what we call coupling or splitting. Bottom line here, if a carbon is attached to n number of hydrogens, the absorbance from that carbon, the NMR signal from that carbon, will be split into n+1 peaks. N hydrogens, n+1 peaks. 2 hydrogens, 3 peaks. Let's see why this is. Let's start off with this good, happy little CH2. When we put this CH2 in our magnetic field, this carbon is either going to orient up or down, isn't it? But so are the hydrogens. Let's pretend that they orient up. That means that we have an increased local magnetic field. We have increased the magnetic field. When we increase the field, we're going to get a larger chemical shift. So that moves it to a higher number. Now, if both of these hydrogens happen to orient down, this is going to diminish our field. When our field diminishes, it moves to a smaller chemical shift. Now we can have 2 degenerate states with an up-down and a down-up. These have no effect because they cancel. So these will occur at the anticipated value for this carbon. What we get is 3 peaks. This one will be in the middle. It will be the most intense because there are 2 opportunities for it. This one will be at higher field, and this will be lower. 2 hydrogens, 3 peaks. This is referred to as a triplet. It is 2, 4 possible combinations. These 2 are degenerate. We get 3 absorbances in the ratio of 1 to 1 to 2. It's a triplet. There's something called Pascal's triangle that describes the expected splitting of a C13. If we have no hydrogens attached, our peak will turn out as a singlet. No hydrogens, nice single peak. If we have 1 hydrogen, we will be split into 2 possibles. Again, they'll be at slightly different chemical shifts. That's called a doublet. 2 hydrogens, we get the triplet, 1 to 2 to 1. 3 hydrogens, we get a 1, a 3, 3, 1. That's a quartet. 3 hydrogens, 4 peaks. Any questions? All right, let's look at toluene. It's a monosubstituted benzene. We've already said that we're going to get peaks here between 120 and 160 parts per million, right? This one has no hydrogens. So that's going to be a singlet, isn't it? 1 peak. This one, which is the same as this one, has one hydrogen. That's a doublet. This one, one hydrogen, it's a doublet. And this guy is also a doublet. For a monosubstituted benzene, we therefore predict that we would have one singlet and 1, 2, 3 doublets in the benzene region. Here's our shifts. Once again, this guy's a singlet. These will show up as a doublet. This is a doublet, and this is a doublet. By looking at that, you can immediately tell this must be a monosubstituted benzene, right? Let's look at a real one. This is for acetophenone. Here we have a carbonyl. Now this is a ketone, but because we've got conjugated with the benzene ring here, it's dropped down just slightly less than 200, and it's here as a singlet. It's a singlet because what? No hydrogens. Here in the benzene region, right around 130 to 140, we have a singlet, that's this guy, and we have 3 doublets, 1, 2, 3. Finally, down here for our methyl group, we have 3 hydrogens. This is a quartet. Now, I know these all look like nice single sharp peaks. We'll see why in just a minute. Once again, this is what's called a proton decoupled NMR. So, what does C13 tells us? The chemical shift will tell us something about the electronic environment, tell us something about the functional groups that are present. Ketones, aldehydes all the way down, then acyl groups, then benzene rings, double bonds, electronegatives, and stuff like that. The splitting will tell us the number of equivalent hydrogens attached to the carbon. N hydrogens, N+1 peaks. All right, here's a real problem then. Look at this molecule. Step 1. I'm not going to say. Decide for yourself. How many peaks do we see in the C13 NMR? Is there symmetry? Of course there is. Split this little sucker right here, right? This half is the same as this half. Down here we have a simple methyl, but it's next to an oxygen, so it's going to be moved down a bit. This is also next to an oxygen, and it's secondary, so it's going to be moved down probably a bit more. We have 2 peaks. This is the CH3, so it's a quartet. This is a CH2, so it's a triplet. 4 peaks and 3 peaks. That's what we predict. Everyone happy with that? 2 peaks in the C13 NMR, a quartet, and a triplet. So, let's do an NMR. Expect this to be 40 to 70, maybe a little higher, 50 to 80, because it's secondary. So let's do our NMR. Well, That's ugly, isn't it? You don't go and yell at the NMR technician because he screwed up your sample. This is what a C13 looks like. Why is it so ugly? Well, remember, there are two things going against you here. This is, in fact, our quartet. If you look at it really closely, there are 4 peaks. There are 3 peaks here, but the noise level is horrendous. That's because low natural abundance. Only 1% of your sample is showing up here. And there's also a problem with NMR sensitivity. NMR sensitivity. In one of the first slides we looked at things lining up with and without, right? Our field. That's referred to as the sensitivity of a nucleus. If you have lots lining up with, lots more lining up with than against, that's very highly sensitive. Carbon-13, you have a tiny fraction of excess with the field as opposed to opposed. So low sensitivity, low concentration, really, really nasty spectrum. Well, with a modern machine, you can run this over and over and over and over again. You collect the data over, several thousand runs, and then you analyze it, you average it, etc., and you can resolve the quartet and the triplet better. What people usually do, however, is something called proton decoupling. Now remember, this splitting occurs because we have these hydrogens that are either with the field or against the field or cancel and stuff like that. The trick here is that the proton and the carbon absorb at different RF frequencies. So you take your sample and with one transmitter you blast it with the frequency, broad spectrum frequency for the protons. That just sends the protons nuts. They go up and down really, really fast. Because of that, it wipes out their contribution for the splitting. All you see now is the carbon. Not only that, but something called the nuclear, here it is, Overhauser effect. Some of the energy that you're pumping into these hydrogens, it's a trickle-down thing. Trickles down into the carbon. This shows up as an enhancement of the signal. Now, the nuclear Overhauser effect is not a linear effect. That means that the height of this signal, the integration, the area under it, is not necessarily proportional to the number of carbons. If we don't do decoupling, it is. But when we do decoupling, this is no longer proportional. So this is actually, let's see, this is our quartet. So this is our CH3, and that's our CH2. They're about the same size, but what you typically see in a spectrum is you will run an uncoupled, determine your splitting, then you will run it proton decoupled, and you will simply identify the chemical shift of the carbons involved. So this means we have a peak at 80, it's a triplet, a peak at about 60, that's a quartet. And that corresponds to the compound that we were looking at, our diether. Any questions? All right, let's go ahead and move forward to proton NMR. Proton NMR. We already know that the proton, the hydrogen, has a spin of 1/2. making it NMR active. The advantage of looking at hydrogens or protons in the NMR is that virtually 100%, 99% is going to be NMR active. The 1% that's deuterium is not, but regular old 1H is. Not only that, but it has a high sensitivity to the NMR, which means we get nice differences between aligning with the field and against the field. This little tiny thingy here, believe it or not, this is an NMR spectrometer. I tried to get the folks here at Triton to buy one. They said they couldn't afford it. But it would be really nice to have one in the lab here. I haven't given up. Believe it or not, this is a real NMR spectrometer. 45 megahertz, permanent magnet, but it's a nice little machine. This is what one looks like in real life. This is a 300 megahertz. Again, it's a liquid nitrogen cooled. Some of them are liquid helium cooled. Your sample goes in here, computer, and blah, blah, blah. All right. Exactly the same thing is going to happen with a proton that happened with carbon. Depending upon the electronic environment, we're going to get absorbances at different parts of our spectrum. Now with carbon, we looked at 0 to 200 parts per million. With carbon, the scale is smaller. It goes from about 0 up to 12 parts per million. Just like we did before, let's go through each of these regions. Remember, we're looking at the hydrogens now, not the carbons. Up here at the top, we have carboxylic acids and we have aldehydes. So these are, this is the hydrogen of the aldehyde, hydrogen of the carboxylic acid. Carboxylic acid are the most highly shifted. They tend to be right around 11. Aldehydes between 9 and 10. This is our double bond region. Benzene rings, very nicely reproducible. Hydrogens on a benzene ring will tend to come between 7 and 8, almost always. Alkenes will be lower than that, typically between 5 and 6. Up top here, we have amide hydrogens, OH hydrogens, and amine hydrogens. And you'll note that these are huge ranges. That's because, just like in the IR, remember we had trouble with hydrogen bonding? We got that big, broad peak due to hydrogen bonding. Well, the same sort of thing happens with these guys. They can hydrogen bond. They can darn near show up anywhere, depending upon the concentration, depending on the solvent, what else is in the mixture, etc. So, and they're usually a little bit diffuse. So these are not really reliable, but they're there. These guys, just like before, when we take carbon-bearing hydrogens next to something electronegative, they're going to typically show up in the 3 to 4 range. So electronegative things move stuff here. If we have a carbon-bearing hydrogens next to a benzene ring, an amine, a carbonyl, double bond, here's an alkyne CH. These things all tend to show up, at around 2.5-ish. They're all going to differ depending upon what's attached. And finally, at the very bottom, just like we had for carbon, we have our simple things. You see there's no steric effect here. They all tend to be right around 1-ish. Interestingly, the one that is the lowest are the hydrogens of a cyclopropane ring. And they're way down here at the bottom. When you look at a real NMR spectrum, you'll also typically see a peak down here at 0. That's a standard. It's tetramethylsilane. And you put that in and then align your machine so this is at 0. That's how you calibrate it. Nice thing about proton NMR is that the area under the peak, that is the integration, is directly proportional to the number of that type of hydrogen. So let's look at this molecule. We have 2 methyl groups, methoxy groups here, and we have a CH2 in the middle. So we have 6 of these guys, we have 2 of these. If we simply look at the relative areas, it comes out 3 to 1. This tells us, if we knew that we had this particular formula, we would say, yes, well, this must be a 6, and that must be a 2. 6 to 2 or 3 to 1. Magnetically equivalent hydrogens will all show up together at the same peak. Any questions? All right, well, let's look at diethyl ether. Look at this and think about what the proton NMR is going to look like. First of all, do we have symmetry? Of course we have symmetry. Split this guy right in half. Our 2 ethyl groups are identical. The methyls on the end are going to be simple. It's an sp cubed hydrogen or carbon. Going to be around 1, maybe a little over 1. We're going to have 3 and 3. Our CH2, this guy is next to the oxygen, so we expect it to be shifted up. Probably going to be closest to 4-ish. The area of this is going to be 2. So since we have 2 CH2s, that would be a 4. That would be a 6. So our lowest would be 3 to 2. That's what we expect. Everyone agree with that? Nice, simple, whatever. Well, let's do the spectrum. Well, gee, there's a lot of peaks there, isn't there? This is splitting in proton NMR. Now, it might make you nuts, but this is extremely useful. This is split into a quartet. This is a triplet. The relative areas are 3 and 2. Our chemical shift, this is, around 1-ish, a little less. And this is a bit less than 4. Why is this a quartet and this a triplet and not single peaks? That's because the signal is being split by the protons on the adjacent carbon. Spin coupling between adjacent hydrogens. I'm sorry, it's my son. Three of them are gone. Last one goes in. This is an example of the peak at 0. This is tetramethylsilane, and it's used as an internal standard because virtually nothing comes this low in the proton NMR. Ethan. All right, why are we getting this coupling? Why are we getting this coupling? Let's look at our compound here. We're dealing with our methyl group here on the end. Let's look at the CH2 that's next to it. Now remember how we said the hydrogens on a carbon were going to split the signal. Here, the hydrogens on the adjacent carbon split the signal. Here's our methyl group. That's the one we're looking at. If both of these hydrogens were oriented with the field, that will enhance the field. If both of them are oriented against the field, that diminishes the field. And if one up, one down, these are in the middle, it has no effect on the field. So the signal from our methyl group sees 3 different electronic or magnetic environments: enhanced, diminished, and in the middle. This is 3 protons, and it's split into, 2 protons, and it's split into n+1 as 3 peaks. Two adjacent hydrogens, 3 peaks. Looking at, this is what a triplet looks like. Again, these 2 are the biggest, and these 2 are small. Quite often, see how these 2 aren't quite the same? Typically, a triplet or a quartet or something will lean towards the thing it's coupled with. Not always, but typically it will. For our CH2, we're adjacent to 3 hydrogens. There are 4 possible combinations, and therefore it's split into a quartet. So this is neat. Here's our spectrum. This is our quartet. That's our CH2 next to the oxygen. We look at the fact that it's a quartet, and we know right away it's next to 3 hydrogens. We look over here at this guy, 3 hydrogens, it's a triplet. We know it's next to 2 hydrogens. Let's look at this in just a little more detail than you probably want to know. The distance between these is actually quite informative. Now, we're not going to deal with this in the lab or anything like that. But how do you know that this guy is in fact coupled to this guy? Well, like I said, these are leaning this way towards it, and these are actually leaning this way towards it. That's one way. The other way is to actually measure the coupling constant. If we label these A and B, the coupling constant is abbreviated as a J. If you measure this distance in parts per million here, between this peak, these peaks, whatever, they're all the same, and they exactly match the coupling constant here to what it's coupled to. So that's how you can actually identify which groups are coupled to which. So let's go through an assortment. Common splitting patterns. I will hush just for a second. Look at these. On this side, we're going to do hydrogens here. This side, we're going to do these that are next to it. Decide what our splitting pattern should be. All right, our first is a CH3. What's it next to? Next to a CH2, isn't it? So this signal is going to have an area of 3, and it's going to be split into n plus 1, that's 3 peaks. Triplet, area 3. The one on this side, this is the CH2, so its area will be 2. It is adjacent to 3 hydrogens, so it will be split into 4 peaks, and again, that's called a quartet. The next one. What's the integration going to be? What's the area? It's going to be 3, isn't it? 3 hydrogens. How many hydrogens is it next to? 1. So it's split into how many peaks? 2. Doublet, area 3. The CH. Area 1, and it's set to 3 hydrogens. 4 peaks, that's called a quartet. We have 2 methyl groups here, but they're identical, aren't they? It's isopropyl. So they're identical. So we're dealing with 6 hydrogens. Our area is going to be 6. How many hydrogens are they next to? 1. So we're going to have area 6. This is going to be split into a doublet. One hydrogen, area 1, right? How many is it next to? because these are identical, it's next to all 6, isn't it? So it's split into a septet. Whenever you have an isopropyl group, this is what it's going to look like. 2. So a nice doublet, area 6, and a septet, 7 little peaks, total area of 1. If you look at an NMR spectrum and you see a doublet and a septet, it's screaming at you, I am an isopropyl group. Look at these, do the same exercise. On this side, we have area 1, 1 hydrogen. What's it next to? 1 hydrogen. So it's split into how many peaks? 2 peaks. And on this side, we have 1 hydrogen next to 1 other hydrogen. It's also split into a doublet, area 1. We have a CH2, so area 2, next to 1 hydrogen. So it's split into 2 peaks, doublet, area 2. 1 hydrogen, area is 1, next to 2 hydrogens, it's a triplet. This guy, 2 hydrogens, so area 2. How many hydrogens is it next to? 2. How many peaks? 3. This one, the same thing. Area 2, next to 2 hydrogens, triplet, area 2. All right, let's take and apply this to benzene rings. We talked about benzene rings in C13. We said we can identify who's what depending upon how many peaks we get, whether they're singlets, doublets, whatever. We can do the same sort of thing to some extent with the proton NMR. Consider this disubstituted benzene, 1,4-disubstituted. These 2 hydrogens are the same, and these 2 are the same, right? So they can behave the same. Hydrogen A is next to how many hydrogens? 1. So this absorbance is going to be split into a doublet. B is next to A, so the absorbance from B is also split into a doublet. What we see looks like this. This isn't a quartet, this is actually 2 doublets. One from A's and one from the B's. There are 2 A's, so the area is 2, 2 B's, the area is 2. Whenever you have unsymmetrical 1,4, it's really, really useful because it's easy to identify what's what. 1,4 substitution, 2 doublets down here in the aromatic region. This is a monosubstituted benzene. Now, you can look at this and say, okay, A should be split into a doublet by B. B should be split by C and A, so that's a doublet of doublets. Again, B is split by A and C, doublet of doublets. C is split by B into a doublet. You should wind up with lots of peaks, shouldn't you? However, the chemical shift of all of these is typically very close. And on most spectra that we'll see, if you have a monosub benzene, you'll just see one peak, area 5. If you had really high resolution, and we'll see an example of that later, you can actually split this up, but at normal resolution, looks like this, one peak, area 5. Again, our shift is right here around 7, where you might expect. Here we have 1,3 disubstituted. Yeah?
Did those hydrogens kind of cancel each other out then?
I'm sorry?
Did the hydrogens kind of cancel each other out then?
They don't cancel, but the chemical shifts are close enough that it just kind of blurs into one big peak. We'll see an example in a little bit where it doesn't, but it just kind of blurs at normal resolution. Here we have unsymmetrical 1,3, bromine and a methyl. So we have 1, 2, 3, 4 different hydrogens, typically with meta-substitution. That's what it's called. You don't see averaging like we did with monosub. What you see is what we lovingly refer to as a multiplet. Multiplet is like a mesoplet. It's lots of peaks, all squished together, really can't figure out what's going on, but the whole group has an area here of 4. 1, 2, 3, 4. So 1,4 is easy. Monosub is easy. Meta, you just get a bit of a mess. Any questions? All right, the instrument that I showed you earlier is a continuous wave NMR. And the spectra that we're going to look at in class are basically all recorded on continuous wave machines. There's a better way to do it these days, and this is called Fourier transform. Fourier transform, FT NMR, this is what you use in C13 all the time, but FT NMR, what you do is you blast your compound with a broad range of frequencies. You excite everything. These protons start to ring, if you will. They go up and down and up and down, absorb, 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 and they decay. It's called a free induction decay. You record that, record the time scale of the decay. What it looks like is something like this. We're going to take this, we're going to pulse it, and we get a unique pattern depending upon how many hydrogens there are, where they are, what the coupling is, etc., etc. Now, you do this pulsing thousands of times. Your computer memorizes the pattern every time. You do noise averaging, and then you do the mathematical operation called Fourier transform, and by George, you wind up with a spectrum. These are monosub benzenes in a continuous wave NMR, they would essentially appear as single peaks, area 5. But the FT allows us to get much more detailed data, and because of that, now you can see all the splitting that goes on all the peaks. Again, we're not going to do this. We're going to do simple CW NMRs because they're much simpler. Any questions? All right, what's our take-home lesson here? What does proton NMR tell us? Chemical shift tells us the electronic environment. Simple, down at low chemical shifts. Benzene's up around 7. Alkenes maybe 5-ish. Electronegative groups between 2, 3, 4, whatever. Chemical shift tells us the environment of your proton. The area, how intense the peak is, the integration under it, tells you how many of that type of proton there are. That's very useful. And the splitting tells us the number of magnetically equivalent hydrogens there are on neighboring carbons. N hydrogens next to it split to N+1 peaks. Pretty much the same we did for C13, except the area in C13 doesn't tell us anything because of the nuclear overhauser effect. All right, any questions? Well, let's look at a spectrum. Here we have a compound, formula C4H8O2. What is it? Now remember back when we did problems in the IR chapter, what was the first thing we did with the formula? We figured out degrees of unsaturation, right? If we had 4 carbons, how many hydrogens do we need? 2n+2. So we need 10. We have 8. We have 1 degree of unsaturation. Either have a ring, carbonyl, double bond. All right, step 2. Let's look at our proton NMR here. We have a quartet, we have a triplet, and we have a singlet. Our areas are 3, 3, and 2. That's 6, 8. My gosh, that's all the hydrogens. Now just look at this NMR. We have this triplet and we have this quartet. Once again, this is screaming at you. I am an ethyl group. I am an ethyl group. Quartet and a triplet. This is an ethyl group. We have a singlet. That means it's a CH3, and it's not next to anything with a hydrogen. All right, let's think about our ethyl group here. This is the terminal carbon, that's our CH3. The CH2 is way the heck down here, isn't it? It's next to something electronegative. What do we have in our compound? We have oxygen, don't I would guess that this is sitting next to an oxygen. In fact, I would say we have this fragment in our molecule. Now, what else are we missing? We're missing 2 carbons, 3 hydrogens, and an oxygen. We know we have 1 degree of unsaturation. By George, I'll bet that's a carbonyl. And our methyl group must be attached to the carbonyl carbon because it's not next to any hydrogens. To get our structure, all we have to do is put these 2 pieces together, and that's what we've got. Ethyl acetate. Now, wasn't that simple? Now you see, if we had the IR, we wouldn't even have to guess, would we? We'd see a big honking carbonyl peak. We'd know right away this is a carbonyl compound. C7H8, how many degrees of unsaturation? 7 times 2 is 14, plus 2 more is 16. What are we missing? 8 hydrogens. How many DUs? 4. Remember my rule of thumb, anytime we have 4 or more degrees of unsaturation, you always think benzene ring. Now let's look at our spectrum. Down here at about 7 parts per million, got what appears to be a singlet worth 5 hydrogens. This is our benzene region, isn't it? This strongly suggests we have a monosubstituted benzene. Down here, just a touch over 2, we have a peak worth 3 hydrogens. 5 plus 3, this is all 8. This is a methyl group. How many hydrogens is it next to? None. Because it has no splitting. This is simple. So what are the parts here? We have a monosubstituted benzene, and this is what it looks like. And what's attached here? A methyl. This is toluene. Any questions? Isn't this fun? Really gets to be fun. Yes, it is. Yes, it is. That's the correct answer. Yes, it is. C8H10. And on this one, I'm also going to give you the C13 NMR. Let's look at both of these. First of all, our analysis. C8. 8 negative 16 plus 2 more is 18. We have how many DUs? We have 4. Once again, we say to ourselves, benzene ring. If we look at our proton NMR, right away here at 7 parts per million. See a peak, little bit of noise down here, but a nice peak, area 5. What does that tell you? Monosubstituted benzene, right? And here we have a quartet and a triplet. What is that screaming at you? It's screaming ethyl group, isn't it? Now let's look at our C13. In our C13, down here in the aromatic region, we have a singlet, 1, 2, 3 doublets. Remember, 1 singlet and 3 doublets was what? Monosubstituted benzene. We also have a triplet, that's a CH2, and a quartet, that's a CH3. Ethyl group, monosub benzene. Put it together. Benzene, ethyl group, proton NMR, singlet, monosub benzene, triplet and a quartet, ethyl group, and this is ethyl benzene. Let me hush for a second, and you guys look at this one and kind of figure out what it might be. All right, look at our analysis. C4, that would require 10 hydrogens. We have 8, that's 1 DU, right? Look at our C13. We have a singlet at 207. What does that tell us? What comes that high in the C13 NMR? That's a ketone, isn't it? We also have a triplet, that's a CH2, a quartet, that's a CH3, and a quartet, that's a CH3. Okay. Ketone carbonyl, We have a triplet and a quartet, that's an ethyl group, and we have a methyl left over. Proton NMR, what do we have? Our triplet and our quartet are screaming what at you? They are screaming ethyl. But we have an ethyl group. This is a CH3, area 3, and it's not adjacent to any hydrogens. Ethyl group and a methyl group, ketone carbonyl, ethyl group, and a methyl. How many ways can you put this together? Start off by drawing your carbonyl. You need an ethyl group on one side, you need a methyl group on the other side, and you wind up with methyl-ethyl ketone. Any questions? Here's another guy. C8H10. H should be 16, 17, 18. We have 4 degrees of unsaturation. Again, that kind of tells you we're thinking benzene ring. For our C13 data, in our region down here, 140 to 125-ish, we have a singlet, doublet, doublet, doublet. That sounds like a monosub benzene, doesn't it? We also have a triplet, that's a CH2, and another triplet, that's another CH2. So we have 2 CH2s. This sounds like a monosub benzene and 2 simple CH2 groups. Any question on the C13? All right. Down here at 7 parts per million, we have a peak worth 5 monosub benzene. That's consistent, isn't it? We have a triplet and a triplet. So this is a CH2 split into 3 peaks, so it must be next to another CH2. This is a CH2 that's also adjacent to a CH2. Only thing that doesn't make sense here is this thing is 1. What in the world is that? One isolated little proton. What could that be? IR shows a big honking peak at 3,400. So what is it? It's an alcohol. And you see how you can use the IR, the C13, and the NMR, take the easy stuff out of each of them, and make a simple spectrum, make a structure. All right, so what we have here, monosub benzene, 2 CH2s next to each other. This guy is shifted up here. It's this one because it's next to the oxygen. These are the C13 shifts, and here's our OH. Couple more. Now this one should be screaming at you already, just looking at the spectrum. We have 5 carbons, 10 hydrogens. We should have 12. That's 1 degree of unsaturation, right? We have 2 oxygens, probably looking at a carbonyl. That's a guess. If we look at our C13 data, is this a ketone or an aldehyde? No. No, it's not. Why do we know that? It's 174, not 200. So this is an acyl. Because we have 2 oxygens, my bet is it's going to be an ester. It's at 174, not 200. It's not an aldehyde or a ketone, probably an ester. We have a quartet, that's a CH3, a CH, and another CH3. Carbonyl carbon, CH3 groups, and a CH. Look at our proton NMR. We have how many peaks here? 1, 2, 3, 4, 5, 6, 7. And we have a doublet. Area 6, area 1. What does that scream at you? What does that tell you? I am an isopropyl group. I am an isopropyl group. So you write down an isopropyl, write down. We have a CH3, that's an isolated methyl. So you write down a CH3 all by itself. What are we missing? 2 oxygens and a carbon. We have an isolated methyl, we have an isopropyl group, and this is our structure. Now the only question that you want to ask me really is, how do you know the oxygen is here and not in between the isopropyl group on this side? How do you know that? I know that, but how do I know it? Look at the shift of our isolated methyl. It's all the way down here at 3.5. So it's next to something very electronegative. This, however, is in the 2.5 region. It's next to the carbonyl, which is much less electronegative. So that's how you know it's a methyl ester and not an isopropyl ester. C9H10O2. 9 is 18. Plus 2 would be 20. We have 10. We're missing 10. That's 5 degrees of unsaturation. That sounds a lot like a benzene ring, doesn't it? All right, if we look at our C13 NMR, we have a singlet at 196. What is that? Well, it's carbonyl. Could be an aldehyde. Could be a ketone. Look here, we have a singlet. Let's see, a singlet at 166. A singlet, okay, singlet at 166. A singlet, doublet, doublet. Oh. All right, well, this is not a monosubbenzene, is it? We have 2 singlets and 2 doublets. Let's see, let's go backwards. I'm too close to this. Quartet, that's a CH3, right? Another CH3. This is at 114, so that's a CH. That's a CH. That's a unsubstituted carbon, and so is that. 2 singlets, 2 doublets in the benzene region.
What about that very first one?
Oh, this is our carbonyl. All right, so it looks like a carbonyl carbon, 2 quartets are methyl groups. Looks like a disubenzene. Now, if we look at a proton NMR, we know that right away, don't we? Look down here in the region between 7 and 8. What do we have? We have 2 doublets. Now, what did 2 doublets down there tell us? That's 1,4 disubstitution. 2 things at positions 1 and 4. 2 doublets on our ring. And we have 2 isolated methyl groups. Now we have 5 degrees of unsaturation, right? 4 of them are the ring. If you add everything up, we're missing a carbon and an oxygen. We know we have a carbonyl. So let's try to put our pieces together. We have 1,4 disubstituted benzene. We have 2 isolated methyls. We have 2 oxygens. 1 has got to be a carbonyl. This guy is shifted way the heck down, so it's probably next to an oxygen, isn't it? This one is 2.5-ish, not really shifted so much. Our structure is this guy. The methyl that shifted way down is this guy right here. The one that isn't shifted so much is next to a carbonyl at 2.5. We have disubstituted benzene. Remember, this CH splits this one into a doublet. This CH splits that into a doublet. 2 doublets down here. Any questions? All right, let's do the game. Oh, how do we know that this is an ester? If it was an ester, this carbonyl would be around 170 and not around 200. So we know it's not an ester. Any questions? All right. I like to call this integrated spectroscopy. And this is what your take-home quiz is going to look like. Okay? You're going to be given IR, NMR, C13 data, and a mass spec for a compound. You will take all of those, take the easy stuff from each of them, and come up with a structure. Okay? Let's see how it works. C8H10. 8 negative 16 plus 2. 16 plus 2, 18. We're missing what? 4 degrees of unsaturation. Sure sounds like a benzene ring to me. Compound has a molecular weight of 106. You're given that. But you know that just by looking at the mass spec. There it is. That's the molecular ion at 106. Now, what's the other thing that stands out in this mass spec? What's the base peak? 91. 91 tells you we have a benzyl group in our molecule. That's the tropylium ion, C7H7 plus. We have a benzyl group in our molecule. (106) minus 91 is how many? 15. This is loss of a methyl group. On your quiz, if you want full credit, all you would have to write is this. Base peak in minus 91, or at 91, suggests a benzyl group, loss of a methyl group from our base peak. That's all you have to write, and you get your points. Our infrared. The way I like to do infrared, and you probably know this, is to start at the top and just work our way down. 3400, do we have an OH peak? Nope, we know what an OH looks like. It's big, it's fat, it's broad. That's not an OH peak. Next, we look just north of the 3000 line. We're looking for sp squared hydrogens. Do you see them? Yeah, real nice sharp peak here. sp squared hydrogens. That's consistent with the fact that we're saying we have a benzene ring. On the low side of 3000, we have nice peaks here. This is sp cubed CH. We don't have an oxygen, but if we did, we would know there's no aldehyde because there's nothing here. We look for triple bonds next. They're here around 21, 22. No triple bond. Next, we look for carbonyls at about 17. That's here. No carbonyl peak. And finally, around 1600, which is here, this little group of peaks is what you kind of expect for benzene ring carbon-carbon stretch. Putting it all together, what does this tell us? A simple substituted benzene.
Wait.
Remember, hopefully this is all being recorded, so if you want to go back and check anything, you can. It should be up on YouTube by tomorrow, hopefully. Here's our proton NMR. Starting down here, 7 parts per million. Nice big peak. Area 5. That's consistent with a monosubstituted benzene. Here we have a quartet and a triplet. What does that tell you? Loudly, I am an ethyl group. Quartet and a triplet. Our CH2 is mildly electronegative. CH3 is not. And we have a monosub-benzene here. Look at our C13. In our aromatic region, we have a singlet, a doublet, a doublet, a doublet. What does that tell us? One singlet, 3 doublets, monosubstituted benzene. We also have a triplet, that's a CH2, and a quartet's a CH3. Again, that's our ethyl group. Ethyl group and monosub-benzene. Go ahead and draw your structure. We have a benzene ring, we have an ethyl group. We have a tropylium ion, which means that there's a CH2 attached to our ring. IR suggests a simple substituted benzene, and of course this is ethyl benzene. Now, if this was quiz day, then we do more here. Take these and take about 5 minutes. And see what you can figure out. Now the quiz that you'll take next Thursday, or I will give you the quiz on Tuesday. Take it home. It will have 6 integrated problems. In order to get credit for a problem, you actually don't have to come up with the correct structure. Okay? But I want you to write all over the paper and tell me everything that you can figure out from each of the spectra. If you don't quite put it together and get the structure, that's okay. I want to make sure that you can interpret this stuff from the spectrum. I will wait 2 minutes and then we'll do the mass spec. How about that? All right, let's look at this formula. 15 carbons, that's 32 hydrogens. How many do we have? 14. How many degrees of unsaturation? 9. Lots of benzene rings here. If a benzene ring is 4, this might suggest that we have 2 benzene rings and 1 more DU. Look at our mass spec. What's our base peak? That's the biggest. The 91. What does that tell you? Benzyl group, right. Now we start here at 210. 119 minus 210, or 210 minus 119 is what? 91. So we're starting at our molecular ion, we're losing the benzyl group, aren't we? We also have a peak here from 119 down to 91. How many is that? That's 28. What 2 atoms that we know and love add up to 28? Well, carbon is 12. What weighs 16? Oxygen. So that's probably loss of a CO. I put a question mark after it because it's a guess. It weighs 28. Lots of things could weigh 28. All right, that would get you full credit for the mass spectrum. There's the IR. Run through your standard peaks. 34, 31, 29, 22, 17, and 16. All right, starting at 3,400, do we have an OH group? Nope. At 3,100. So on the high side of 3,000, yeah, we got a really nice sp squared CH. At 2,900, we got kind of a little sort of thing. Probably a sp cubed CH. Do we have a triple bond? Absolutely not. 1,700. Whoa, now that says Carbonyl, doesn't it? 1,700, we have a nice, big, happy Carbonyl. Look at 1,600 and below. We kind of recognize these. These are the peaks we see for benzene, carbon-carbon stretching. So what does this look like? Benzene rings and a carbon. Not an aldehyde, is it? Because there's no aldehyde peaks right here. So writing this down gives you full credit for the ion. That's the simplest way, very systematic. Our NMR data, we have C13 and we have proton. Let's do our proton first. We have 14 hydrogens. Look at our integrations. We have 5, 6, 7. So everything's doubled. So we have 10 in the benzene region, and we have 4 down here. This kind of looks like 2 probably monosub-benzenes. Bit messy, but that's what it looks like. That would give us 10 hydrogens. Our CH2s, are they adjacent to any other hydrogen? No, they're not. They're isolated. We have a peak for a CH2 and a multiplet down here for a monosub-benzene. Now look at your C13 NMR. Singlet at 208, what does that tell you? Well, it's all the way up at the top. It's a ketone carbonyl, isn't it? We already knew that from the IR. Aryl ketone. Look here in the benzene region, 139 down to 125. We have a singlet and 3 doublets. That's the signature of what? Monosubstituted benzene. And we have CH2. Ketone carbonyl, monosubbenzene, and a CH2. All right, put these together. Again, you get full credit. This is all you have to give me. The structure is optional, but it'll drive you crazy if you don't get it. Start with your ketone carbonyl. We have benzene ring and a CH2. What else are we missing? We're missing 7 carbons and 7 hydrogens. What does that mean is on the other side here? The same thing. Dibenzyl ketone. Big tropylium, split off the benzyl group. Once you split that off, you can lose CO and make another tropylium ion. The proton NMR is kind of split up because you got an awful lot going on here. These guys are feeling the presence of the carbonyl and each other, so the splitting is a little enhanced. That's why it turns out to be a messy book. A little bit messy, not a nice thing. Nice clean CH2s. Again, symmetry on both sides. Now, remember at the start of the class, I showed you on the organic interactive where you could go and work problems if you like. There's also the entire text of practical spectroscopy on Blackboard. There are lots of problems in that. You can go to the McMurry site and you can look at spectra. They're interpreted for you. You can do the organic chemistry online old. Now I apologize that it doesn't fit nicely on today's monitors. If you make your screen little like they used to be, it looks better. But there are lots of problems there. Again, integrated problems, nice practice. And of course, this is all recorded, so you can listen to it over and over and over again. Isn't that exciting? All right, that's it for tonight. Our lab for next Tuesday is actually going to deal with